Hi, everyone, and welcome back. We are going to go ahead and talk about gravitation today. So let's go ahead and start with Newton's law of gravitation. Now, he went ahead and made some observations when two objects were near each other. Okay, so say we have two objects in space. He started thinking about what makes them attract, say, like us to the Earth. What is going on there? Okay, so he came up with this idea of the law of gravitation. Okay, so he made some observations. Say, for example, we have two spherical objects. Okay, those are the whole objects, these spheres here. And we have their center of masses calculated out. Okay, and from each of those center of masses, they are separated by some distance r. Okay, so this is the separation distance here. And we have their masses. And he noticed that there is a force between those two, or a couple of forces between those two objects in order to make those objects attract. Okay, so just like us to the Earth, okay, we aren't just floating in space, right? We are drawn to the Earth due to the gravitational pull of Earth. Okay, now we have this in every object. Okay, so like yourself to your computer, or even yourself to the calculator, there is some sort of gravitational attraction that is going on, but it's just not large enough for us to feel. Okay, so we can't, I don't know, it's not some kind of futuristic weird thing, right? That we've got some kind of force between these objects and then they can come together really easily. But he noticed that these forces must be super, super small. Okay, so he started coming up with some kind of equation in order to determine what these forces could be. Okay, so he knew that this equation has to do with the mass of both of the objects, so he added that into his equation. He also noticed that as you pull something further away or closer together, that these forces changed. Okay, so he also knew that it had to be related to the inverse of r squared. Okay, so that distance between their center of masses. Okay, so let me just write down that r is the distance between the centers of mass. Okay, and with that, again, he knew that this had to be a really small factor, okay, or else we would have us and like our calculator, or us and our computer attracting to each other through gravity and, you know, be like smooshed together. But this doesn't happen. So he knew that this had to have some sort of constant, and he called it G involved. And so now we call it the universal gravitational constant. And somebody else came up with that value, and that value is 6.67 times 10 to the negative 11th Newton meters squared over kilogram squared. So this person was able to calculate that through this work. Okay, so now with that, we want to be able to look at different situations and describe their motion. Okay, so we can determine the motion caused by gravitational forces by first identifying the two masses for which you want to find the gravitational force. Okay, then draw a free body diagram, and you want to make sure you sketch the forces that are acting on each mass. Okay, and indicate the distance between their centers of mass, so r. And then you want to apply Newton's second law of motion to each mass to determine how it will move. Okay, so let's go ahead and put this into action. Let's start with example 13.1. It states consider two nearly spherical Soyuz payload vehicles in orbit around Earth, each with mass 9,000 kilograms and diameter of 4.0 meters. They're initially at rest relative to each other, 10 meters from center to center. So from center of mass to center of mass. Determine the gravitational force between them and their initial acceleration. Then estimate how long it takes for them to drift together and how fast they are moving upon impact. So let's go ahead and start with this first portion, determining the gravitational force between them. So that is going to be some F12 or object 1 to object 2. Or I'm sorry, I forgot to explain that back here. So these different forces here, we have F12 and F21. So let me describe what those mean, okay, these subscripts here. So F12 means that this is the force, force on mass 1 due to mass 2. Okay, so it's a little bit counterintuitive, but this is the force on this object 1 due to object 2. Okay, and same thing over here. This is the force on M2 due to M1. Okay, so that's important to note here. Okay, so let's go back. And now we're going to say F12 is going to be G M1 M2 over R squared. And for now, since we are not worried about the direction, we're going to go ahead and drop the vector notation. Okay. Now, we said that each mass is 9,000 kilograms. So I'm going to say M1 is equal to M2, which equals 9,000 kilograms. Okay. We also said its diameter of each is going to be 4 meters. Then we said the distance from center of mass to center of mass is 10 meters. So I'm going to call that R is equal to 10 meters. Okay. All right, so let's go ahead and plug everything in. So G is going to be 6.67 times 10 to the negative 11th Newton meters squared over kilograms squared times our masses. So we have 9,000 kilograms times 9,000 kilograms. Oops, another 0. And sorry, my pen is kind of being funny. So if my handwriting is terrible, I'm not sure what's going on, other than the pen isn't picking it up correctly. Divided by our radius squared, so, or our distance. So that's 10 meters squared. Okay. So if we put that into a calculator, we find that our force is 5.4 times 10 to the negative 5th newtons. Okay, so that is the force on 1 due to object 2, and they will be the same, and we'll see why a little bit later. Okay, at least the magnitude will be the same. Okay, so this is our gravitational force, and we want to know their initial acceleration. So remember that F is equal to mass times acceleration. Okay. And so we can just solve for our acceleration by dividing our mass. So we have F over M. So our acceleration should be 5.4 times 10 to the negative 5th newtons over our mass, which is 9,000. And notice that we are looking for each of their acceleration. Okay, each of their accelerations. So this is going to be the acceleration of one of the vehicles. Okay, so we take that value, divide it by 9,000, and we get an acceleration of 6.0 times 10 to the negative 9th meters per second squared. Okay. So that is the initial acceleration. Okay. Now we want to estimate how long it takes for them to drift together. Okay. And also how fast they are moving upon impact. So we have a couple of equations from the past that we can use. For that second part, we'll go ahead and start with that one. We have that velocity squared is equal to the initial velocity squared plus 2 times the acceleration times x minus x naught. Okay. Now, let's see. For them to drift together. So we have the distance from each of their center of masses. Okay. So we want to know now what is the distance for them to drift together. Okay, so that's going to be this distance here, or that displacement. Okay. So let's see. We were given that each of these have a diameter of 4 meters, meaning that their radii, so R1 is equal to R2 is equal to 2 meters. Whoops. Okay, right? Because radii is 1/2 of the diameter. Okay. So let's see. If we take that into account, sorry, I'm trying to think in my head. So I've got 2 objects, boom, boom, with some radius, and then we know this distance here, but for them to collide, it's just going to be this distance, right? So we need to take that total distance, so that's 10 meters, and subtract out each of the radiuses, radii, radii, not radiuses, okay? So it would be 10 meters minus 2 meters minus 2 meters. So that should be 6 meters, right? Okay. Then we know that these were initially at rest relative to each other. So V naught is 0. Okay. And we're trying to find the velocity. Our acceleration we just solved for, 6.0 times 10 to the negative 9th meters per second squared. So from this, we'll need to square root both sides. Okay. So let's go ahead and say our acceleration times 2 times 6, and then square root that. And we get the velocity is equal to 2.68 times 10 to the negative 4th meters per second. Okay. Now with that, we can find our how long it takes for them to actually drift together. So we have this equation, V equals V naught plus AT. And then that again is 0, our initial velocity. So then we can solve for T. T is going to equal V divided by A. Okay, so let's go ahead and do that. We'll take our V here that we just solved for, divide that by our acceleration. So 6 times 10 to the negative 9th. And we get 4.47 times 10 to the 4th seconds. Or we can put that into hours. Let's go ahead and do that. So for 1 hour, there's 3,600 seconds, right? So divide that by 3,600, and we get 12.4 hours. Okay. All right, I know that I had to smush it in here, but hopefully you guys were able to follow. Let's go ahead and get started on the next one. It's going to be very similar to this one. So this is example 13.2. We want to find the acceleration of our galaxy, the Milky Way, due to the nearest comparable sized galaxy, the Andromeda galaxy. Okay, the approximate mass of each galaxy is 800 billion solar masses. Okay, and they're separated by 2.5 million light years. Okay, each galaxy has a diameter of roughly 100,000 light years, and we have the conversion here. Okay, so again, we're trying to find the acceleration. So first, we'll need to determine our force. Okay, so again, that's going to be G times M1, M2 over R squared. Okay, and we will also set that equal to M times A. Okay, and we're going to call M1 our mass, but it doesn't really matter because they're about the same mass. So we're going to say A is going to equal G M2 over R squared. Okay, and G is 6.67 times 10 to the negative 11th Newton meters squared over kilograms squared. Okay, our second mass, I don't have that number on me, so I'll have to look that up. So 800 billion, so times 10 to the 9th, I believe, yeah, times our solar mass, so M solar. Let me look that up in our textbook. Actually, is it right here? The mass of the sun is 2 times 10 to the 30 kilograms. So 2 times 10 to the 30 kilograms. So we've got 800 times 10 to the 9th times 2 times 10 to the 30th. And that's going to give us 1.6 times 10 to the 42nd kilogram. So this value is going to go right there. Okay. And then we divide that by our radius. So our radius is 2.5 million light years. Okay, so we've got 2.5 times 10 to the 6th light year. And so for each light year, we've got 9.5 times 10 to the 15th meters. Okay, so we've got 2.5 times 10 to the, 10 to the 6th times 9.5 times 10 to the 15th. So we get a radius of 2.38 approximately times 10 to the 22 meters. And again, we're going to square that. So let's go ahead and do that. And we will take, it's going to be 6.67 times 10 to the negative 11th times 1.6 times 10 to the 42nd divided by 2.38 times 10 to the 22nd squared. And we get that our acceleration is 1.89 times 10 to the negative 13th meters per second squared. Let's double check that that is correct. And it is. Okay. Oops. Okay. So we can go ahead and move on to acceleration due to gravity. I'm actually going to go ahead and pause here and then start with the next video here, okay?